Every day, thousands of industrial boilers quietly generate the heat that powers modern civilization. They produce the steam used to manufacture food, medicines, paper, chemicals, textiles, and countless other products we rely on. Yet most of these boilers still burn fossil fuels, making them one of the largest sources of industrial carbon emissions. As industries search for cleaner alternatives, a new solution is emerging: hydrogen boilers. These systems promise to deliver the same high-temperature heat while significantly reducing carbon emissions when fueled with low-carbon hydrogen. Today, we'll follow the complete journey of a hydrogen boiler, uncovering the hidden engineering that transforms hydrogen into industrial steam. Behind the walls of an industrial plant lies the boiler house, the heart of the entire heating system. This is where fuel, water, automation, and safety systems come together to produce the energy that keeps factories operating around the clock. Every pipe, valve, pump, and sensor has a specific purpose. Although it may appear to be a maze of equipment, everything is carefully arranged to maximize efficiency, reliability, and safety. Before we follow the flow of energy, we first need to understand the machine at the center of it all. At the center of the boiler house stands the industrial hydrogen boiler. From the outside, it looks like a massive pressure vessel wrapped in insulation and surrounded by piping. Inside, however, is an intricate engineering system designed to transfer enormous amounts of heat into water. Unlike residential boilers that heat buildings, industrial boilers generate large quantities of hot water or steam for manufacturing processes. When powered by hydrogen instead of natural gas, the fundamental objective remains the same: produce reliable industrial heat, but with the potential for dramatically lower carbon emissions. The real engineering story begins inside this steel vessel. Before hydrogen reaches the burner, it must pass through the gas train. This system carefully prepares the fuel for combustion. Pressure regulators ensure hydrogen arrives at the correct pressure. Isolation valves allow operators to safely shut down the system. Filters remove contaminants, and flow control devices precisely meter the amount of fuel entering the boiler. Hydrogen behaves differently from natural gas. It burns faster, has a wider flammability range, and requires specialized combustion controls. Every component in the gas train is designed to deliver hydrogen safely, consistently, and accurately to the burner. The burner is where chemistry becomes usable energy. As hydrogen mixes with carefully controlled amounts of air, an ignition system initiates combustion. The burner must create a stable, efficient flame while minimizing pollutants such as nitrogen oxides. Unlike conventional burners, hydrogen burners are engineered specifically for hydrogen's unique combustion characteristics. Sophisticated flame geometry, airflow management, and combustion controls ensure that the flame remains stable while delivering the immense heat required for industrial steam production. This single component determines much of the boiler's efficiency, reliability, and environmental performance. Once ignited, the hydrogen flame burns inside the combustion chamber. Temperatures quickly rise to well over 1,000 degrees Celsius, creating an intense environment where chemical energy is converted into thermal energy. The chamber must withstand these extreme temperatures while directing the hot combustion gases through carefully engineered pathways. Modern materials, refractory linings, and precision engineering protect the pressure vessel from thermal damage while maximizing heat transfer. This is the point where hydrogen's stored energy is fully released, beginning its transformation into useful industrial heat. Creating heat is only the first step. The true purpose of the boiler is to transfer that heat into water as efficiently as possible. As hot combustion gases flow through the boiler's fire tubes or around water tubes, thermal energy moves through the metal walls into the surrounding water. Engineers carefully design these heat exchange surfaces to maximize efficiency while minimizing energy losses. Every additional percentage of heat recovered reduces fuel consumption and operating costs. Although invisible to the human eye, this continuous movement of thermal energy is what makes industrial boilers among the most important heat transfer machines in modern engineering. After leaving the steam drum, the steam enters the collection header, where multiple steam flows are combined into a single controlled distribution network. This header acts like the central highway of the boiler system, ensuring a stable pressure and consistent steam supply before the energy leaves the boiler house. Every valve, pressure gauge, and control device continuously monitors the steam to maintain the precise conditions required by the manufacturing process. Even small pressure fluctuations can affect production quality, which is why the steam header plays such a critical role in delivering reliable thermal energy. Now the steam begins its journey throughout the facility. Large insulated pipelines transport enormous amounts of thermal energy from the boiler house to different production areas. Unlike electricity, which travels through cables, steam physically carries heat through these pipes. Heavy insulation minimizes heat loss, while expansion joints allow the piping to safely expand and contract as temperatures change. From the outside, these pipelines may appear simple, but they form an extensive energy distribution network that quietly delivers the heat required to power modern industry. The purpose of the entire boiler system becomes clear once the steam reaches the production floor. Across food processing plants, pharmaceutical facilities, chemical factories, paper mills, textile manufacturers, and countless other industries, steam provides the thermal energy required for heating, sterilization, drying, cooking, evaporation, and chemical reactions. It is one of the most versatile forms of industrial energy. Every product moving through these production lines depends on carefully controlled steam delivered from the boiler. Without it, much of modern manufacturing would simply stop. After transferring its heat to the manufacturing process, the steam cools and condenses back into water. Rather than discarding this valuable resource, engineers capture it through the condensate return system. This hot condensate still contains significant thermal energy and has already been treated to remove impurities, making it ideal for reuse. Returning condensate reduces water consumption, lowers fuel requirements, and improves overall plant efficiency. Instead of beginning the heating process from cold water again, the system continuously recycles its own energy, creating a highly efficient closed-loop process. Before fresh feed water enters the boiler, it passes through one of the most effective energy-saving devices in the entire plant, the economizer. Hot exhaust gases leaving the boiler still contain valuable heat that would otherwise escape into the atmosphere. The economizer captures this waste heat and transfers it into the incoming feed water, reducing the amount of fuel required to reach boiling temperature. This simple but highly effective heat recovery process significantly improves boiler efficiency and lowers operating costs. It is a perfect example of engineering design to recover energy that would otherwise be lost. One of the greatest hidden threats inside any boiler is oxygen dissolved in the feed water. Even tiny amounts can cause corrosion, shorten equipment life, and reduce system reliability. The deaerator removes dissolved oxygen and other non-condensable gases before the water enters the boiler. Using controlled heating and steam contact, unwanted gases are separated and safely vented away. By protecting the boiler from internal corrosion, the deaerator helps ensure decades of reliable operation while reducing maintenance costs and preventing unexpected equipment failures. Industrial boilers operate under high temperatures and pressures, making safety an absolute priority. Safety relief valves continuously stand ready to protect the system. If pressure rises beyond safe operating limits, these valves automatically open to release excess steam, preventing dangerous overpressure conditions. This protection requires no operator intervention. It is a fully automatic safety mechanism built directly into the boiler design. Along with flame monitoring, gas detection, pressure controls, and emergency shutdown systems, relief valves form part of a comprehensive safety strategy that allows hydrogen boilers to operate reliably in demanding industrial environments. Safe and efficient boiler operation depends on continuous measurement. Pressure transmitters, temperature sensors, flow meters, and level instruments constantly monitor every critical operating condition throughout the plant. These instruments transform physical measurements into digital information that operators and control systems can use to make real-time decisions. If pressure changes, water levels fluctuate, or steam demand increases, the instrumentation immediately detects the change. This continuous stream of data allows the boiler to respond automatically, maintaining stable operation while maximizing efficiency and protecting equipment from abnormal conditions. Collecting data is only valuable if the system can respond to it. Throughout the hydrogen boiler plant, hundreds of intelligent sensors continuously monitor pressure, temperature, water level, hydrogen flow, steam flow, flame stability, and equipment health. Every second, these sensors generate thousands of measurements that provide a complete picture of the boiler's operating condition. If a parameter begins to move outside its optimal range, the control system reacts almost instantly. This invisible network of sensors forms the nervous system of the entire boiler plant, allowing it to operate safely, efficiently, and reliably with minimal manual intervention. Although we've explored each subsystem individually, none of them operates alone. The burner, combustion chamber, heat exchanger, steam drum, condensate return, economizer, deaerator, safety systems, and instrumentation all function as one integrated machine. Every change in steam demand triggers adjustments throughout the entire plant. Fuel flow increases, combustion adapts, feed water pumps respond, valves reposition, and control systems continuously balance the process. This coordinated operation transforms dozens of individual components into a single intelligent energy system capable of delivering reliable industrial heat around the clock. While much of the plant operates automatically, engineers oversee everything from the central control room. Large SCADA and distributed control system displays provide a real-time digital representation of the entire boiler operation. Operators monitor steam production, hydrogen consumption, temperatures, pressures, equipment status, and safety alarms from a single location. Advanced software continuously analyzes performance, identifies potential issues, and supports predictive maintenance before problems occur. Rather than manually operating individual valves, modern engineers supervise highly automated systems that can respond to changing process conditions in real time. By this point, the entire hydrogen boiler plant begins to come into focus. Hydrogen enters through the gas train, combustion releases thermal energy, heat is transferred into water, steam is generated and distributed to industrial processes, condensate returns for reuse, waste heat is recovered, and intelligent automation coordinates every step. What first appeared to be a collection of pipes and machinery is actually a carefully engineered energy ecosystem where every component contributes to efficiency, reliability, and safety. The true power of the system lies not in any single machine, but in how every subsystem works together. A hydrogen boiler is only one part of a much larger industrial energy network. Steam production connects with process equipment, water treatment systems, automation platforms, hydrogen supply infrastructure, electrical distribution, and plant-wide energy management. Every subsystem exchanges information and energy with the others. Sensors communicate with controllers, controllers adjust equipment, and equipment responds to changing production requirements. This continuous interaction allows the facility to operate as one synchronized system, maximizing efficiency while maintaining consistent product quality and safe operation. Stepping back even further reveals an interconnected industrial ecosystem. Hydrogen storage, fuel delivery, combustion, steam generation, condensate recovery, heat recovery, instrumentation, automation, and manufacturing processes are all linked together in a continuous cycle. Energy is transformed, recovered, monitored, and reused at every opportunity. This systems-level perspective highlights an important engineering principle. Modern industrial efficiency comes not only from better equipment, but from designing every component to operate as part of an integrated whole. Perhaps the easiest way to understand the entire plant is to follow the energy itself. It begins as chemical energy stored within hydrogen molecules. Combustion converts that chemical energy into thermal energy. The boiler transfers thermal energy into water, creating steam. Steam transports that energy throughout the factory, where it powers industrial processes before condensing back into water and returning to the boiler. Along the way, waste heat is recovered, operating conditions are monitored, and the entire cycle repeats continuously. This invisible journey of energy is the hidden process that powers countless industries around the world every single day. What began as a single industrial building has now been revealed as an extraordinary network of engineering systems working together with remarkable precision. Hidden behind walls and beneath layers of insulation are combustion technologies, heat exchangers, pressure vessels, pumps, sensors, automation systems, safety equipment, and sophisticated control software. Most people never see these systems, yet they quietly produce the steam that supports manufacturing, healthcare, food production, and critical infrastructure. Understanding these hidden machines gives us a new appreciation for the engineering that keeps modern society running. Hydrogen boilers represent one possible pathway toward reducing emissions from industries that require high-temperature heat. While challenges remain, including hydrogen production, infrastructure development, fuel cost, and large-scale deployment, the engineering foundation already exists. As cleaner hydrogen becomes more widely available, hydrogen-fired boilers could become an increasingly important option for decarbonizing industrial steam generation. Whether they are used alongside heat pumps, electrification, biomass, or hydrogen fuel cells, one thing is clear. The future of industrial heating will depend on innovative engineering and integrated energy systems. Thank you for watching. If you enjoyed this documentary and want to explore more of the hidden systems powering our world, subscribe to Renee Energy. We simplify complex engineering through cinematic visual storytelling, helping you understand the technologies shaping the future of clean energy.